So welcome everyone from around the world. It's a great pleasure to have Giles Gardam as our speaker today in the Semi-Algebra and Geometry Online seminar. And he's going to tell us about how to solve semi-decidable problems in group theory.
Thanks very much for the invitation. It's a real pleasure to be here. So today I want to talk about how to solve some problems in group theory, or at least how to try and solve them. I'll start with saying what I mean by semi-decidable problems, and then get into some examples and some situations where we have certain strategies and tricks that work out. So this is sort of material from a paper in preparation. The key success story here is producing a counterexample to the Kaplansky unit conjecture. But that's not the only example of where these methods can apply. So the talk will be very focused on the computational side of the story. So if you have seen me give a talk about the Kaplansky conjectures before, there'll be very little overlap with that talk. So I guess that's good news. And if you're someone who doesn't usually tend to think or work computationally, I still hope that you'll come away from this talk having learned something new, something interesting. Okay, so I'll start with some computational complexity 101, or maybe in the local jargon 1001. So when I say computational complexity, we start talking about algorithms, maybe the first thing that comes to your mind is the famous P versus NP question. So this asks, can every decision problem, so a question where we have some input and our algorithm needs to answer yes or no to answer some question, can each decision problem for which the yes answers can be checked in polynomial time, in fact, be solved in polynomial time? So when I say checked, I mean, if we have the answer in some sort of certificate that verifies the answer, is that something that our algorithm can check in polynomial time? So yeah, P stands for polynomial time. The N stands for non-deterministic, which is sort of another way of formulating this, saying essentially that our algorithm can luckily guess exactly what the certificate of the answer looks like. So you've probably heard of many examples of famous problems from the class NP, and particularly of NP complete problems, which are some of the maximally difficult questions in this class. For example, the traveling salesperson problem. The best image for which I could find in an image search online was actually an XKCD comic. So I'll just chuck that in here. So I guess there aren't too many traveling salespeople hitting the road these days, but the question still remains. Given a graph, a weighted graph, can we find a path that visits every vertex in the graph using at most some certain cost? So can we visit all the cities traveling at most 1,000 kilometers, say? So if the answer to this decision problem, can we do it in under 1,000 kilometers, is yes, then the certificate is just the path. And this is something that we can verify very quickly. We just check that the path visits every city and check that the total length is less than 1,000 kilometers. But we're certainly very far from being able to say whether just given the graph we can find such a path, or say that it doesn't exist in polynomial time. So this is sort of maybe what we first think of with computational complexity questions, like is something solvable in polynomial time, or what complexity, quadratic, cubic, and so on. But in group theory, a lot of questions just lie way beyond this complexity class. In fact, way beyond things like problem solvable in exponential time or doubly exponential, in fact, beyond decidability. So there are plenty of questions which are just algorithmically undecidable. There's provably no algorithm that will answer the question for us. But on the other hand, a lot of questions are at least half or semi-decidable. So a problem is semi-decidable if there's an algorithm that will terminate and give us the answer yes when we're given an input for which the answer is indeed yes. But otherwise it might run forever. Okay, or maybe it'll stop after some time and say no. But at any rate, we only have a guarantee of termination on the positive inputs. Okay, so so semi-decidable, only half of the problem is decidable. For the other half, we don't really know what's going to happen. So equivalently, we could say that the language of all the yes inputs is recursively enumerable. So standard mathematician's trick, I could just say, take that as a definition of recursively enumerable. But what I really mean by recursively enumerable is that there's an algorithm that will just spit out all those, the elements of that set one after another that will enumerate them. So to go one way, say I have my partial algorithm, as I'll call it, which answers the semi-decidable problem. So an algorithm that will only stop half the time. Then out of this, I can create an algorithm that enumerates all of the S inputs just by trying every single possible input imaginable. And whenever doing sort of a big diagonalization procedure where I'm trying in parallel to run each of the possible inputs for longer and longer, everything that has a yes answer will eventually pop up. And then I output that. So these are sort of equivalent ways of thinking about something being semi-decidable. And I want to stress that if a problem is semi-decidable but not decidable, then it really means I have absolutely no way of saying how long it takes to get to a yes answer, right? If I had a computable upper bound on how long it takes to return a yes answer, then once I've hit that bound, I can just give up and say, okay, the answer must be no. And that would then give me a way of deciding the answer to the question. So in the cases where we know something semi-decidable but not decidable, it's not just that we don't know how long it takes, there cannot be any computable upper bound on how long it takes. So certainly there's just nothing we can say essentially. So here's some classical examples of undecidable problems in group theory. Perhaps the most famous is the word problem for groups. So this goes back to Novikov-Boone in the 50s. So this says there's a finitely presented group, so one fixed finitely presented group for which we can't decide its word problem. And the word problem means given a word, so some product of generators and their inverses, or equivalently some element in the free group on the generating set, can we decide if that is actually the trivial element or not in the group? So this is undecidable. It is, however, semi-decidable. The fact that it's semi-decidable is easy to see. That's just, well, by definition, essentially, the word is trivial in the group if and only if I can write it as some finite product of conjugates of relators and their inverses. Okay, and the set of such expressions, sure, it's some countably infinite set, but it's certainly a set that I can enumerate. I can try all expressions up to a certain length with all u's up to a certain length and repeat this for bigger and bigger bounds. If my word is trivial, eventually I'll find such an expression. So in other words, if the word is trivial, I have this very naive algorithm, which will eventually, who knows when, but will eventually find a proof that that word is indeed trivial. So just to emphasize, in this case, the group is not part of the input. The input's just the word. The group is fixed in advance. And even for certain groups, we cannot do this. And of course, there are many nice groups for which we do know how to solve the word problem. But in full generality, there are groups for which this is an undecidable problem. There are also questions we can ask where the group presentation is the input. So the triviality problem for presentations is similarly undecidable. I can't decide, given an arbitrary presentation of a group, is that the trivial group or not? If it is the trivial group, though, I can eventually produce a proof of this just by essentially using my solution to the word problem to try and prove that each of the generators is trivial. And if the group is trivial, then each of the generators is trivial, and eventually I'll be able to prove that using this approach from the word problem, which, okay, although the word problem's a problem where the presentation is fixed, this enumeration of the words that represent the trivial element is obviously something I can do given the presentation as input. Okay, but of course, maybe in some cases, I can answer this question even if the answer is no, the group is non-trivial. For example, I can always compute the abelianization. So if the group has non-trivial abelianization, then I'll be able to say, oh, this is not the trivial group. But otherwise, there's no general way for me to decide that a group is not the trivial group. Okay. And one final example that I like, just because it's the opposite flavor to these first two. Okay, so I've put it under the heading classical problems. It's maybe a classical problem that has a fairly recent solution. And that's what's called the profinite triviality problem for group presentations. So is the profinite completion of a finitely presented group trivial or not? Or in other words, given a presentation of a group, can I decide, does that group have any non-trivial finite quotient? The reason I like this is that it's, okay, so Bridson and Wilton proved that it's undecidable, but it's easily seen to be semi-decidable. And the half of the problem that we can do is actually the non-triviality direction. So that's why I like it. It has the opposite flavor of the other two. If there is a non-trivial finite quotient, eventually we can find it, say by enumerating all maps from our generators to finite symmetric groups, and for each of them checking if the relations in the group are satisfied. If they are, then we've got an actual group homomorphism. Okay, so those are some very classical undecidable problems, just to give you a sort of flavor of various things in group theory that we certainly can't decide in general. So I think whenever we have any question, it's always worth asking ourselves, is this something that I can approach with computation? Is this, say, a semi-decidable question? Is there any way I could hope to bring computation to bear on this? I think probably it's most interesting questions we ask ourselves won't be decidable, in the sense that at least that there's an easy way that we can come up with to run a computer to try and to try and answer the question in either direction. But maybe it's at least semi-decidable, and maybe that's especially the case if we restrict focus. So perhaps we want to answer a question by producing a counterexample, and maybe all possible counterexamples that would be, within the rules of maths is just a bit too crazy for us to try and get our hands on. But maybe if we restrict our focus on specific types of counterexamples, then it becomes easier to try and think of how we can produce them by computation. So the key example, key success story in this paradigm for me is the unit conjecture. This goes back to Hugman's thesis from 1940 and was popularized by Kaplansky in a paper from 1970. It was also sort of independently known in the USSR. So the question is, given a torsion-free group in a field, are the only units in its group ring the trivial units? So recall that the multiplication in the group ring is sort of just this obvious product that linearly extends multiplication in the group. So every element of the group ring is just a finite formal k-linear sum of group elements. The product is sort of just determined by saying we have the distributive law, and if I multiply two elements supported at single group elements, then I just multiply the group elements according to multiplication in the group and multiply the field elements according to multiplication in the field. So units are things which are invertible on the left and the right, and anything that's of the form kg, so where this formal sum is a sum of length 1, that's clearly seen to be invertible because I can just invert the group element and invert the field element. So there's always these trivial units floating around, and the conjecture says that, in fact, they should be the only units in the group ring. So we now know that this is false. And I sort of think this is fitting into the paradigm of semi-decidable questions, because if I at least assume that my group has a solvable word problem, and let's also say that our field is finite, just to avoid questions about how I enumerate elements of the field and whether I can compute in the field or not. So if we make these restrictions, at least for simplicity, then the set of non-trivial units is a recursively enumerable set, something where there's a fairly naive algorithm, at least, that will just spit them out one after another. And that's just because, my group ring is some countably infinite set. I can enumerate elements of them because they're all just supported on some finite number of group elements with this choice of the field coefficients. So I can enumerate the whole group ring one after another. I can therefore enumerate all pairs of elements, alpha and beta, and I can then check for any pair, is their product 1? Is alpha beta equal to beta alpha equals 1? Okay, so the consequence of this is that the existence of non-trivial units is semi-decidable modulo the word problem. So if you give me a generating set of a group and some oracle that will solve its word problem for me, then say at least with finite field coefficients, I can just go along and attempt to produce a non-trivial unit. If one exists, I'll eventually stumble into it. And then I can say, okay, there are non-trivial units in this group ring. Okay. So saying that this set of non-trivial units is recursively enumerable isn't really saying anything at all, of course, because even the empty set is recursively enumerable. I guess the algorithm there just spins its wheels and doesn't spit anything out. So we haven't necessarily made progress, but we at least have like a conceptual framework of how you can think about this. Right. Yeah. So yeah, as I said, I'm really focusing on the computational side of the story, so I won't really get into how the unit conjecture fits into other parts of maths, but maybe I should just quickly say that it's related to some other conjectures of Kaplansky, and certainly these other conjectures are known to be related to other questions from various things like operator K-theory, algebraic K-theory, L2 invariance, and so on. The unit conjecture was somehow a bit of an odd one out and wasn't really known to relate to many other questions in maths, and I guess the fact that it's false maybe sort of explains why no one ever succeeded in relating it to any other big questions. Okay, so if we commit to the belief that this recursively enumerable set we're trying to enumerate is non-empty, then it's now a matter of how can I work through that set quick enough that I'll actually produce at least one element from that set before the end of the universe. I think if we're going about this sort of a good paradigm, we're trying to find essentially a needle in an infinite haystack. I think a good approach is to turn our infinite haystack into an infinite sequence of finite haystacks. So there's certainly cases where trying to say produce elements with some random procedure can be quite fruitful. But if we're in a situation where random approaches just don't work because the probability of some random grouping element being a unit is very low, for example, then I think it can be very helpful to try and turn to a sequence of finite questions that we can conclusively answer, and then try and answer bigger and bigger subproblems. I think there's a lot of reasons why this is a good approach. If we have a sort of random search that we run for a period of time and we don't find anything, then we're not really that much wiser at the end of it. At least if we answer some finite subproblems, we come away being able to say conclusively something like, I know there's no counterexample to this conjecture within these bounds of how big it is, for example. And something else that's really nice is that you can then think about different ways to try and answer your finite subproblems and compare them. Right? I might have possibility A and B, and I can see how quick they are at answering these finite subproblems and use that as a way of guiding my general approach. So for groups, sort of a natural choice of how to divide a lot of questions into subproblems is to just take finite sets in the group, take a filtration by finite sets, and I think sort of the not very inspired but very natural choice is to take balls in a Cayley graph. So in other words, fix a generating set and say, look at all words that I can write down using at most n generators in their inverses, and do that for increasing values of n. So here's a nice picture of a Cayley graph, the picture I found online that best sort of captures what I think of when I think of a Cayley graph of an infinite group. This is actually a Cayley graph of a Grigorchuk group, which has torsion, so it's definitely not something relevant for the Kaplansky conjectures because everything's torsion-free. But I think this captures the spirit of this growing graph that looks somewhat like a tree, but certainly has lots of loops in it as well. Okay. Right, so I said whether there is a non-trivial unit is semi-decidable because if I'm given two group ring elements and I know how to compute in that group ring, then I can just check if their product is 1 or not. But of course, it's not just an abstract statement. You know, I can check them somehow, and eventually I'll figure out if the product's 1 or not. If I say assume that I can solve the word problem quickly, then this is something I can also check very quickly, right? As long as I'm not stuck with a group where it's difficult to compute. Say my word problem in the group is solvable in polynomial time, then I can also check in polynomial time if two group ring elements multiply to give 1. So this has the flavor of NP, right? It's this situation where I want to find some answer, and if I had such an answer, I could verify it very quickly. So let's sort of abstract away the word problem in the group completely and get a very concrete instance of an NP problem. Namely, let's say I take as input the multiplication table for two finite subsets in the group G. So subsets A and B, and for each pair of an element in A and an element in B, I know what that product is in some normal form, say. And I guess I probably also want to know what the identity element looks like in G. But just with this finite chunk of combinatorial data, I then want to decide, do these sets A and B support a non-trivial solution to alpha beta equals 1 in the group ring over some finite field? So yeah, maybe a quick remark. Usually I'll just say, let's solve alpha beta equals 1 and forget about the other equation beta alpha equals 1. Usually there are reasons why we know that 1 already implies the other. So in finding our units, we just need to find things that are invertible on one side. In fact, if this weren't the case, it would actually be a more interesting answer anyway. So I'm just going to try and solve alpha beta equals 1. Okay, I've now got this question in NP. If I have my, I'm given this set of data, if there is a non-trivial unit that's supported on these sets, then it's something I can check very quickly, just using the multiplication table. Okay, but of course we don't know if we can solve problems in NP in polynomial time, and we certainly need to ask quite big questions before the answer is yes. So the non-trivial units that I found were in what's called the Hunch event group. This is a crystallographic group. So up to passing to a finite index subgroup, it's actually just Z cubed. So it comes with a free isometric action co-compact on Euclidean 3 space. And if we're just taking bigger and bigger balls in the Cayley graph and asking, do they support a non-trivial unit, then we have to go to radius 5 before we get a solution. And this ball, okay, I guess these balls have moderate growth. I mean, it's actually cubic, so sort of asymptotically things aren't too bad, but still, by the time we get to radius 5, we already have 147 elements to consider. And 2 to the 147 is 10 to the 44, which is just way beyond what we could possibly do any sort of brute force computation if I'm trying to enumerate all elements in the group ring, say over F2 supported on this ball. Right, so a computer can do something like the order of 10 to the 9 very basic operations per second. So, you know, even in 10,000 years, this is still like 10 to the 20, I think. So 10 to the 44 is just way out of reach. But certainly, there's a lot of interest in problems in NP. And it's not just pure mathematicians such as myself who find themselves wishing it would be really nice if we had fast solutions to problems in NP. There's all sorts of real world applications for which we want to do this. So thinking along the lines of traveling salesperson problem, we can of course imagine there's lots of optimization questions, logistics and so on, where we want to solve questions which are instances of an NP complete problem, but also for various things like hardware and software verification, if we want to check that there aren't bugs in code or verify that a circuit functions the way it's supposed to. These are all things that can be formulated in NP. And as a result of this, there's a range of industrial tools to try and solve various different NP complete problems. So natural question at this point is, well, I have this problem in NP I want to solve. Is there some industrial tool that will do it for me? Martin Bridson is fond of saying that computer science is the new physics. The spirit here is that the interaction between maths and computer science, the same way that the interaction between maths and physics has been in the past, is really a two-way street. And not only do we prove theorems which are of interest to computer scientists also, I guess, have intuition, theories, and tools which are useful for mathematicians. Okay. So in this case, there is a really nice NP complete problem for us to use. And in fact, it's the oldest NP complete problem in the book. And this is Boolean satisfiability, which is generally just referred to as SAT. So SAT was the first problem proved to be NP complete. So a priori, there's no reason why NP complete problems need to exist at all. It could be that there are incomparable problems in class of NP which are harder than any, But Cook and Levin in the early 70s proved that this is NP complete. So technically that means any problem in NP can be reduced in polynomial time to an instance of SAT. Okay, what is SAT? Well, it just asks, given a Boolean formula in propositional logic, so this is, if you like, 0th order logic, there are no quantifiers like exists or for all. It's literally just a formula involving some finite number of variables. We ask, is there an assignment of those variables to true and false that makes the whole formula evaluate to true? That is, we say it satisfies the formula. So this formula is some big expression in Boolean logic that is a combination of our variables using things like and, or, not, implies, exclusive or, and so on. So here, the instance to the input in this decision problem is the formula. So I just want to sort of stress that the size of the formula is relevant. How we actually encode our problem is important. And we're not just talking about, is this something that's solvable in certain time compared to the number of variables, say. And in fact, a formula is just a way of, it is a way of encoding some function from these assignments to the set true or false, or 0, 1. Perhaps I should say false, true, 0, 1. And there's 2 to the 2 to the n such functions. So certainly, in order to encode them in general, I can't get away with encodings that are, say, polynomial in the number of variables. In general, some of these will need exponential size to even formulate them. Okay. So the standard encoding that we use to express a formula in satisfiability is so-called conjunctive normal form. And conjunction just means and so conjunctive normal form is just a big and of ors. So if my variables were x, y, and z, I could have something like this expression which just says x or not y. That has to be true, and not x or y or z has to be true, and y or not z. So this is, of course, very small and easy to answer, and it's, of course, satisfiable, even just for, I guess, counting reasons. So yeah, if you're not familiar with this specific notation, it's very reminiscent of set theory for natural reasons. Intersection is like and union is like or. Negation is like complement. So just some quick terminology. Each of these factors in the big and is called a clause. So something like x or not y is the first clause in this expression. And literals are either variables or their negations. Okay, so if I'm given a formula that's not in this normal form, some more complicated nested expression, I can still turn it into something in conjunctive normal form of linear size in the input using sort of very standard procedure called the Zayton transformation. The cost of this is that I have to introduce new auxiliary variables. But if I didn't do that, then actually I'd sort of necessarily have short formulas which require exponentially big conjunctive normal form expressions. Okay. Yeah. And there are tools that can do this for you as well. Yeah, so maybe I should just quickly say a bigger formula isn't necessarily harder. There's no like one-to-one correspondence between size of a formula and how difficult the problem is. But certainly the size of the formula is something relevant, and maybe on average, we expect that bigger things are harder to solve. And certainly the worst case bounds get worse, especially as the number of variables grows. Okay, so how do I turn my existence of non-trivial units into a question in SAT? So for simplicity, let's just say I'm going to work over F2. I could do other finite fields. It's just a lot more messy, and it's just not as nice, and I guess a lot less manageable for various reasons, but it's certainly possible. I can have some binary encoding of those finite fields and the arithmetic of that field. Okay, so let's say we're going to try and find a solution supported on the ball of radius n. Fix my grouping element alpha is just this sum of alpha GG, and beta is sum of BGG. So alpha G and BG are our field coefficients. Now I'm just trying to solve some quadratic system of equations over the field. And this is the way I turn it into SAT. So first I want to assert that my solution is non-trivial. So the easiest way to do it, which I'll just do here, is to say, well, up to translating things around in the group, which, okay, technically could affect whether or not we find solutions supported on the ball of radius n or not, but let's not worry about that. Up to translation, I can assume that my non-trivial unit is supported at the identity. So I'll just add a clause of length 1 saying that this coefficient A1 is non-zero. Right, so on this slide, I'm abusing notation a lot and going back and forth between thinking of these coefficients that we're solving for, AG and BG, being either elements of the field on two elements or being Boolean variables. So false is 0 in the field and true is 1 in the field. And so I want to assert non-triviality by saying I'm supported at the identity element, so A1 equals 1, which as a Boolean clause is just the length 1 clause A1. And I have to have some support elsewhere, so I just have this big OR of all of the other A variables. Okay, so that's non-triviality out of the way. Now I need to say that the product alpha beta is equal to 1. I'm trying to assert that some quadratic system of equations is satisfied. So the first thing I do is introduce quadratically many variables to encode each of the products of an AG and a BH. And so I want to introduce in a variable XGH to carry this product in the field of AG and BH, which in terms of Boolean logic is just saying that I want XGH to be the AND of those two variables. So I'm sure it doesn't surprise you that I can put this in conjunctive normal form. And the way I enforce this is this constraint that I've written here. Perhaps a bit more transparent is it's not the thing in conjunctive normal form, but the line below it, which is equivalent. So the clause saying not X or A is exactly the same thing as saying that X implies A. And so I'm saying if X is non-zero, then both A and B have to be non-zero. And then the third clause says, well, if A and B are both non-zero, then X has to be non-zero. So this is my little conjunctive normal form expression, which enforces the constraint that X is the AND of the A and the B. Okay. So now I just need to say that the right sums of these variables, of these X variables, gives me either 0 or 1, according to whether I'm calculating the coefficient in the product alpha beta of the identity element or something else. So each of them, so for each group element K in the ball of radius 2n, I'll have an equation that has to be satisfied. So this sum is just saying what the coefficient of K is in the product. And that needs to be 1 if K is the identity element and 0 otherwise. So that's why I've put this like Kronecker delta here. So each of these equations can be asserted by breaking it up into smaller subsums. So I introduce auxiliary variables, which will store like partial sums, if you like. And then I get all these small atomic equations that I want to assert by themselves. So say of length 3 or 4. For example, if I have this equation x plus y plus z equals 0 in the field, which is saying in logic that I have an exclusive or sum being false. Well, okay, this is, in terms of linear algebra, of course, we're now thinking, okay, this is some solution to this equation. It'll be some codimension 1 subspace. We know that there are exactly 4 solutions out of the 8 possible points we have. So there are 4 choices of x, y, and z that don't satisfy this equation, and we can just ban them all one by one. Okay, so x, y, z equals 1, 1, 1 is not a solution of this equation. And the way I ban that solution is to say not x or not y or not z, this first clause. So for each of the 4 possibilities of bad choices of x, y, and z, I add a clause which excludes exactly that possibility. Okay. And that's it. Now we've encoded the existence of non-trivial units, at least over F2, into SAT. So something that I really want to stress here is that I've made my problem a finite problem by fixing the size of the ball in the Cayley graph. And I asked this question to the SAT solver. But beyond this fact that I've sort of fixed the ball, SAT no longer cares at all how big the support of the unit it's trying to find actually is. The reason why this approach succeeds is sort of dependent on the fact that SAT solvers are very powerful. But this is sort of like a very, this is a qualitative difference between this approach and some approaches that I think other people have tried in the past, which sort of explains why other approaches didn't really have prospects of success. So the smallest unit that I know that exists in a torsion-free group has support of size 21. And trying to enumerate 21 element subsets of 147 elements, this is just crazily big. And there are other approaches to try and prove this sort of by considering all possible ways that the terms in 2 grouping elements could multiply to give 1. And you can sort of write down a presentation of a universal group where certain, where you have units in a certain way. And this approach sort of can be used to prove there are no non-trivial units where both alpha and beta have support of size 5. And so sort of already trying to do this at size 7 is sort of, the combinatorics is already completely unmanageable. So to then go up to like size 21 is just completely impossible. But the SAT solver doesn't actually care how many of these variables are turned off or on. It's sort of completely agnostic about what's going on. It doesn't know whether it's trying to solve something in a group ring or if it's trying to, mine for Bitcoin or something like this. It has no idea what it's actually doing. And so this is why we're able to produce units which have very large support, which seems to be necessary. Okay. Of course, turning the existence of non-trivial units into SAT is all very well, but we need the fact that it's still a problem that we can solve at the end of the day. Best case, we can't say anything better than exponential time. So why is it that we can actually do this? Well, I mean, modern SAT solvers are really, really fantastic. I just have to say it's crazy how powerful these tools are. I guess it's no secret in the computer science world that SAT solvers are great, but I think this community really deserves some sort of rock star status. And I guess I regret that if by not talking about this sooner, I've not really been actively helping that. But now it's time to make amends. So SAT solvers are really great. At the heart of it, they're building, most of them are building on the so-called DPLL algorithm from 1961. This is a very old school AI, if you like. Davis and Putnam are names you might recognize from their contribution, along with Robinson and Matiasevich, to Hilbert's 10th problem. This algorithm is a backtracking algorithm with some basic deductions. So backtracking means we're going to try assigning variables to true or false and see what happens, how the formula simplifies, and then recursively make more and more assumptions until we either find a satisfying assignment or realize that we've made a mistake, and then we go back and try again. So a sort of recursive call tree. And we have some basic deductions, unit propagation, pure literal elimination. Okay, so for example, if I had this toy example from the previous slide, if I set x to be 0, so set x to be false, then my first clause, x or not y, is now just not y, because x is false, it's not going to help me satisfy that clause. But my middle clause, not x or y or z, that vanishes because it's satisfied. Okay, so each time I make an assignment, my conjunctive normal form expression will get simpler. So on this left-hand branch here, where I set x to be false, I now have a clause which is just length 1, saying not y. Okay, so I now know at this point, certainly y has to be false. So I might as well, I don't need to try 2 possibilities at this point. I just know I can set y to be false and continue from there. And after I set y to be false, I then know that in the second expression, this will simplify to not z. So I then know the value of z. So this is what's called unit propagation. Whenever I see a unit clause, a clause of length 1, I learn something straight away. I can substitute that in elsewhere and then see how far I get by propagating this. Again, the pure literal eliminations, something we can do on the right-hand side. Each of the clauses only involves a y. There's no clause that involves a not y. So y is a so-called pure literal because it only occurs with this polarity. So I know I don't lose anything by setting y to be true. There's no possible downside to saying y is true. Okay, so building on this very old school AI foundation, modern SAT solvers use very sophisticated heuristics to try and choose when to, which variables to split on. They have very optimized data structures to do everything very quickly. And they also have this new paradigm of, which is sort of a more recent development called conflict-driven clause learning, essentially saying once we hit some conflict where I realize I can't go any further and I have to backtrack, I try and learn something out of that by trying to see what part of that assignment is actually causing the problem. Okay, so putting these together with all sorts of tricks, optimizations, heuristics, they can handle problems which sort of seem completely unimaginable before 2000. So bigger doesn't necessarily mean harder, and it's always important how difficult your problem is at the core of it, not just how big it is on paper. But SAT solvers can handle some questions where you have hundreds of thousands of variables and millions of clauses, for example, which, of course, in terms of exponential brute force, this is completely absurd. Right, so you might have heard of previous applications of SAT solvers in maths, especially to Ramsey theory, where there's a real, I guess, very clear how a lot of Ramsey theoretic questions can be phrased in terms of SAT. For example, what was in 2016 the world's longest proof, which is a computer-generated SAT proof weighing in at 200 terabytes, that was produced by Höhler, Kuhlmann, and Marek, answering the Boolean Pythagorean triple question of Ron Graham. So they proved that there's no two coloring of the positive integers without a monochromatic Pythagorean triple. So this is very readily encoded as a problem in SAT. Once we fix the set, a finite set of positive integers we're trying to assign colors to. In fact, they showed this problem is unsatisfiable on the set from 1 to 7,825. But I should emphasize these Ramsey theoretic applications of SAT have a very different flavor from what I'm doing here with producing non-trivial units, say, because they have, I guess, it's the same as the qualitative difference between trying to prove a theorem and trying to find a counterexample. They have this problem which is easily solvable when we have small instances, and they take bigger and bigger problems until they get to the point that the answer is the system is unsatisfiable. I'm instead I start with small problems where there's no solution to the system of equations, I look at bigger and bigger problems until I hope eventually I get to a satisfiable system. And certainly, I think I have the feeling that site communities, like a lot of the applications tend more to be in this direction of trying to prove systems are unsatisfiable in say, software verification or hardware verifications would be proving that there's no bug or proving that there's no way your circuit can be somehow corrupted. So in that spirit, you would say that producing a non-trivial unit is like finding some bug in your code or some glitch in the matrix. Okay, so why is the non-trivial unit something that we can do with SAT? I mean, how hard is it even? So it's kind of difficult to say how difficult a problem is, because especially when you're asking a question where the answer is this system is satisfiable, this is very sensitive to how exactly you formulate the problem, which solver you use. Does it get lucky exploring the search space very early on or not? So depending on exactly how you formulate this question of producing non-trivial units, you might get an answer in space of a few minutes or a few hours or maybe days. The SAT community is constantly innovating and producing better solvers. They have an annual competition where all the solvers compete to see who can solve problems the fastest. But even say sort of a very a recent but not super recent SAT solver, MiniSat 2.2, which was released in 2010 and is roughly what was the state of the art in 2008. The solver, say, can solve this encoding that we gave on the previous slide. So actually we can restrict to having one of the units on the ball. So yeah, we can actually put the unit on the ball of radius 4 if we allow its inverse to be on the ball of radius 5. And that problem it can solve in about a day. If I adjust the formulation slightly and say forget about asserting what happens at the identity element, although I'm still essentially asking the same question mathematically for not really transparent reasons, this now is something that terminates in like 9 hours. Certainly more recent SAT solvers can get answers quicker, but this is not really something that is dependent on innovations from the last decade. And why is this a problem that is somewhat amenable to SAT solving? Why is it not sort of worst case for a problem of its size? So I think a key factor that this problem has is that the system we're trying to solve is very sparse in some spots. So in meaning that the equations we have are quite short. So I think it's something like 10% of the equations of length 3 or less. And if I have an equation of length 2, meaning there's some element in my ball of radius 2n, which I can only write as a product of two things in the ball of radius n in exactly 2 ways, well then, so I would get such an equation of length 2, which means as soon as I know that one of those contributions is non-zero, I know the other is non-zero, and therefore I have another 2 terms which I know have to be non-zero as a result. So with these very short equations, as soon as something's non-zero, it forces lots of other things to be non-zero, and this can propagate and is likely to very quickly lead to a contradiction and will let me learn certain things like that at least one of these 2 variables has to be false. So I think in general, it's a very difficult problem to look under the hood of a SAT solver and really argue about why it's effective or not. But I think it explains part of why this problem is not too difficult for SAT solvers. So the natural question at this point is, well, what other problems can we apply SAT to? So certainly all these questions on this slide, which live around the unit conjecture. So there's 2 Kaplansky conjectures that are weaker than it, the zero divisor and idempotent conjecture. And in the top row, there are some group theoretic properties that are stronger than the unit conjecture. All of these things admit nice encodings into SAT, and I'll say something about that now. I guess the proviso on that is that this property diffuse I won't say anything about, because actually it's something that we can solve in polynomial time with a greedy algorithm. So that's in a paper of Kionke Rambo. I guess they don't call it a polynomial time greedy algorithm, but that's what it is. Okay, so maybe the first question we're going to ask now is, well, what about the zero divisor conjecture? So asking for a unit and asking for a zero divisor only differ by saying, is this product going to have coefficient 0 or coefficient 1 at the identity element? So really, it's the exact same question up to flipping a single bit somewhere. It's readily apparent that we can ask this question. So why am I not telling you about zero divisors today? So I guess there's multiple reasons. One, maybe the zero divisor conjecture is just true. We have to consider that possibility. I guess another important reason is that we have a real shortage of candidate groups. So for the unit conjecture, there was sort of one canonical, easiest possible candidate group to work with. For the zero divisor conjecture, okay, there are some the sort of small cancellation approaches which give candidate groups, but these are things that are not very amenable to actual practical computation with a computer. So after we discard them, there's sort of 3 papers giving some concrete, explicit, short presentations of candidate groups, which overcome this unique product property obstruction that was on the previous slide. But all of them are actually known to satisfy the zero divisor conjecture. So there just aren't really any apparent candidate groups to try. And any candidate group will necessarily be quite big in various senses. So, okay, certainly in terms of the growth of balls in the Cayley graph, it will have to be bigger than polynomial, probably exponential. And we also think in terms of the presentations, the presentation of this group with non-trivial units, those relations are length 6, which says, which means that if I take the ball of radius 3, I can already see those relations. These little loops of length 6 will fit inside the ball of radius 3. I go out to something of length 3 and then come back. So already quite early on, I can see all of the group theory in a sense in quite a small chunk of that group, some quite small ball. Whereas probably we can't expect that any candidate counterexample to the zero divisor conjecture will be similarly compact. So probably not only do the balls grow much faster, probably necessarily need to go much further. Right. So that's sort of reasons why the zero divisor conjecture remains a challenge. So now, what about this unique product property? So the definition is, well, it's sort of what it says in the name, that we have unique products. So the property says that for all finite subsets A and B of the group G, there's some element of the group which is uniquely expressible as a product of an element A from A and an element B from B. This is certainly only true for torsion-free groups, because if we have any finite subgroup, I can just set A and B to both be that finite subgroup, and then this property will fail straight away. Maybe a good example to have in mind is the integers. The integers have the unique product property because if I take this finite set A and finite set B, I can just take the maximum element from A, maximum element from B, and certainly their group theoretic product, which is their sum in integer arithmetic, will be this unique product of the product set. And so we can formulate the failure of this problem as a cardinality constraint. So I've sort of used some ideas for this binary encoding from a paper of Fish and Beugner's. This is just a very nice way of putting into conjunctive normal form the constraint that says, if I look at these X variables corresponding to a given group element that I had before, now instead of trying to assert that their sum is 0, I'm trying to assert that either I'm trying to say I'm not allowed to have exactly one of those be true. So I have to either have none of those X variables be true, or I have to have at least 2. Okay, and this is something we can express in quite a nice way. So if we do this and also apply a few ahead of time deductions to try and simplify the problem, it's possible to at least get some new groups without the unique product property. So at least I can say we're not completely stuck in terms of trying to get new candidate counterexamples for Kaplansky conjectures. Okay, so here's a group that I made this work for. I've given a two-generated, two-related presentation to just emphasize that this is something small and explicit, but that's certainly not the best way to think about this group. The best way to think about this group is more in terms of its cat-zero geometry. This is acting freely co-compactly on an A2 tilde building, if you're familiar with buildings. So there's all sorts of consequences for the group, meaning that it's nice in lots of senses, but it also has property T, which is a very desirable property to have, say, if we want counterexamples to the zero divisor conjecture, because this rules out most of the tools that we have to prove the zero divisor conjecture. And at least as far as I know, none of the methods for proving the zero divisor conjecture work for this group. So just a quick remark on sort of the scale of the problem that we have to work with here. So the smallest ball where we find this failure with unique product property is the ball of radius 6. That already has 1,311 elements. So we're quickly getting into the territory where we have millions of variables in our problem. And so we're getting very quickly close to the cusp of what is really possible or not with current tools. Now, the ball of radius 4 is a tree, and this is because, so the shortest length of a relator in this presentation is length 9. And in fact, something stronger is true, which is that the shortest word, which, so the shortest non-empty reduced word, which is the identity element in this group, is indeed length 9. There's no surprising shorter relations. So that means that the ball of radius 4 is a tree, because there's no relations of length 8 or shorter. So this tells me immediately that if I am only looking at sets A and B supported on the ball of radius 2, then the multiplication table I get is exactly what I get in the free group. So by comparison with the free group, I know straight away that I have to at least go to radius 3 in order to find such a counterexample. And okay, it turns out we need to go twice as far as this very naive lower bound. We have to go out to radius 6. Okay. Right, so orderability is also something that we can formulate in terms of SAT. So a group is left orderable. Okay, there's also some equivalent notion of right orderable. They're really the same thing. If there's a total order in the group such that it's invariant under left multiplication. So for every h and k, one of them's bigger than the other, and if h is less than k, then gh is less than gk, or for all ghk. So sort of folklore fact, I think probably a lot of people knew this, certainly not quite this statement, but the spirit of it is in a paper of Nathan Dunfield. Non-orderability is semi-decidable modulo the word problem. So if you give me a group which is not orderable and an oracle that will solve its word problem for me, eventually I'll be able to produce a proof that that group is not orderable. Okay, so why is that? The easiest way to think about this is to, instead of thinking about the order comparing pairs of elements, let's just think about comparing single elements to the identity. So we'll talk about the positive cone. Defining an order is equivalent to choosing the positive cone, which is just a set of elements bigger than 1. And the constraint on such a set to be the positive cone of an order is just that it, together with the set of its inverses, together with the set containing the identity element, has to be a partition of the group. Right? Everything's either the identity or it's positive, or it's negative because its inverse is positive. And P has to be a subsemi group closed under multiplication. If I multiply two positive things, I have to get something positive out. Okay, so I just have sort of, I want to choose such an assignment of things as positive or negative, which satisfy certain constraints, namely that, yeah, if I multiply two positive things, I get something positive, for example. If my group is not orderable, then there has to be some finite set that witnesses this, where already on the finite set, it's not possible to do this. So in model theory, they just say this is compactness. I guess really the, I don't know, another way of saying it is if I have some way of assigning the group elements to positive and negative that works on any finite subset of the group, then I can consider all these assignments and put them into, say, some inverse system. And if I have an inverse system of non-empty finite sets, then the inverse limit will be some non-empty compact set. Okay, so if I find some finite chunk of the group where this is not possible, I know the group's not orderable. In fact, if the group's not orderable, I'm guaranteed to eventually find some finite chunk where already on this set, I see it's not possible to consistently assign things to positive and negative. And okay, it's not just something that we can answer in some amount of time. I mean, this is something that we know is in NP. If I create a variable for each group element to record, is it positive or not? Then I get all these clauses, say for GH and GH. So let's assume that these are not the identity element. Then I get a clause like, so not XG or not XH or XGH that says if X is positive and H is positive, then their product has to be positive. And the other clause is saying the same, but for negative. Okay, so non-orderability is semi-decidable, and all these finite subproblems that we ask are actually instances of 3-SAT, and something that we can very readily answer using SAT solvers. So 3-SAT just means that it's a SAT problem where all the clauses are length 3 or less. And this, the fact that we have this 3-SAT problem was actually used by OLF to show that random groups in the triangular model are non-orderable. So this problem seems to, in practice, be solvable very, very quickly on any instance that I've ever tried it. I can't say anything conclusive about how this really performs compared to other approaches to prove that groups are non-orderable. So, for example, a paper of Caligari and Dunfield turns this sort of folklore fact into an algorithm to try and prove groups are non-orderable. And certainly Dunfield has applied this to prove lots of groups are non-orderable. I know that there are some examples where his approach didn't work, or the computer gave up at some point, where using SAT I can answer it, but this is sort of just cherry picking a few examples out of tens of thousands of groups. So I don't really have a conclusive comparison between this and other methods, but certainly it seems to be very powerful. Okay, and so finally, since the method to produce non-trivial units is so general purpose, perhaps it's not so surprising that it does work at least on one more group. So in Lindsay Solberg's master's thesis, she introduced this torsion-free polycyclic group, which I'll call S. It has this very short presentation. And the way this group arises is from trying to find very small failures of the unique product property. So you sort of say, let's consider the presentation of some universal group such that it doesn't have the unique product property because I have these 8 elements and those 8 elements, and when I multiply them together, they pair up in this way. So yeah, we fail to have the unique product property with these 2 8-element sets. This is the current world record, so to say. It's not necessarily the best possible, but it's the best that we know. And what is this polycyclic group group theoretically? So up to finite index, it's actually the Heisenberg group, which is the free 2-generator 2-step nilpotent group. Yeah, and so it's a bit harder to find non-trivial units here than in the Hunch event group. The group, I guess we need to go a bit further. I mean, we need to consider more elements. And the smallest one I know is a bit bigger. So this group ring has non-trivial units. For example, here's one which has support of size 29, which is the shortest I know. So I have to say I don't really know very much about the units in this group ring other than that they exist. And this is an example of one. Okay, so that's all I wanted to say. I'd be very happy to answer any questions.
Can I ask about the example you had where the unique product property doesn't hold? Is this a Kaplansky group?
I'm not sure. So Ronan has sort of 4 universal groups. So if you take one of them, you can pass to, I mean, sort of in the graph of groups description, we have a retraction onto the vertex group, which sort of, we can simultaneously retract the whole onto all of the vertex groups in a sense, meaning that we have an index 21 subgroup that's torsion free. And then I then take a index 3 extension of that subgroup, which I think comes from symmetry of the defining triangle. So that's how the group arises. So it is arithmetic, for example. It's very nice in many senses. Yeah.
So Giles, it seemed like your way of searching for non-trivial units prioritized the, I mean, if I can put it like that, the length of the elements involved as words in the generators. Is there any similar way of searching that would prioritize the length of the number of non-zero coefficients, the length of the expression itself?
Certainly one could add constraints to the problem that you pass to the SAT solver, which say, I want to find an answer where the size of the support is at most 20 or 19 or something like this. So you could try and find things with small support that way by sort of directly asserting it. In terms of an approach that somehow looks through the group in a different way to prioritize this, I think you'd really need some very good idea of what you're looking to try and cook up such an approach. I guess I don't have any ideas of how one could try and do that.
I have a sort of frivolous question. How long did it take the computer to find the counterexample on the final slide? If that's a well-posed question, I don't know.
That is a well-posed question. I'm sorry, I don't actually remember.
Okay.
So, like, is it a group theory that's specifically good for these sorts of problems, or do you see like SAT solvers as being useful in other algebraic areas?
I think there's just a lot of untapped potential for all sorts of mathematical questions. I mean, whenever you have something which at the heart of it is you're asking questions about very explicit finite combinatorial sort of things, then it's possible that you can turn that into a question that a SAT solver can understand. So this arithmetic over F2, it's pretty clear how to turn that into something that a SAT solver understands. But I mean, you can also tell a SAT solver that you want to find a graph with certain properties or all sorts of things. If you're willing to work hard enough, you can boil down to a question about Boolean satisfiability. So yeah, I have to say I'm really coming from a group theoretic background. So this is why I'm so focused on group theoretic questions, but I think there's probably potential for applications in all parts of maths.
You were prepared to make a guess at this point about the zero divisor conjecture, at least over F2. So
certainly the zero divisor conjecture seems like it should be not as hard as the idempotent conjecture. I mean, I think there's a big difference between those two. And without any reason why it should be true, I think I'm willing to believe that there should be counterexamples. But yeah, the question is, are they really things that we're capable of getting our hands on with current tools? I think probably this is more requiring mathematical innovation than SAT solving innovation. We need group theory to tell us which questions to ask rather than just needing more powerful tools to answer those questions. How feasible something is very sensitive on what the question you ask is. And I think the SAT community continues to innovate and make their SAT solvers better and better, but I think there's more potential for more rapid improvement by thinking about what questions we ask them. So yeah, to answer your question, I think it should be possible, but it certainly doesn't look like it's low-hanging fruit. But yeah, anyone who has ideas is very welcome to get in touch with me, of course.
Well, at least for mathematicians, that's a hopeful note to end on. Please join me in thanking Giles again for his very interesting talk.
Thank you. It's my pleasure.